Today we are going to discuss the topic vapor pressure of liquid-liquid solution under the chapter solution. Vapor pressure of liquid-liquid solution. As you know, solution is a mixture of solute and solvent, and you know that solvent is a part of the solution which is in excess and the solute is a part of the solution which is in less amount. So we will take the liquid-liquid solutions, means both the solute and solvent will be liquid. In this topic, in this chapter actually, we will discuss about the binary solution. Binary solution. What is binary solution? Which is made up of only two components. That is, only one solute will be taken. And of course, the other will be solvent. We have to discuss the vapor pressure of liquid-liquid solution. So it means both the components of the binary solution should be volatile in nature. That is, they can convert into the vapor phase. Now, before going to discuss about the vapor pressure of liquid-liquid solution, we should know what is exactly vapor pressure. As you know, if we take any liquid in an open vessel, then this liquid will gain heat from the surroundings, and after some time what we will observe, the level of the liquid surface will get low. Suppose this was the initial level and it is the, after some time the level is this, right? Why the level of the liquid get decreases? Because of the evaporation. So you know the evaporation. In evaporation, the molecules at the surface level of the liquid escapes out. But what if the liquid is kept in a closed container? If we keep this liquid in a closed container, and what will happen? The vapors which escape from the surface of the liquid, they won't be able to escape out of the container. It means the vapors will be in the container only. So these vapors will strike with the surface of with the walls of the vessel, with the lid of the vessel, and they get they will lose the energy and the condensation process will occur, and these vapors will get converted into liquid, and similarly the process will be going on. Means the liquid will be converted into vapors and vapors will convert back into the liquids. Now if we put an experimental setup, suppose we do this experiment in a thermostat. Thermostat means we, at a particular temperature, if we allow this process to occur, and we connect this whole experimental setup with the pressure gauge, right? This is suppose pressure gauge. Okay, so after some time, when the process of evaporation and condensation is occurring, what we will observe, after some time the pressure gauge shows a particular pressure. It means the pressure becomes the constant. Why? Because the vapors which are escaping out, they are converting into the liquid. At a particular stage, what will happen? The liquid and the vapors, they will be at equilibrium. It means after some time we will get a state of equilibrium. So these vapors which are above the liquid surface, they will start creating pressure, and that's why we will get a particular reading in this pressure gauge, right? So now you can define the vapor pressure. What is vapor pressure? Vapor pressure. So vapor pressure is the pressure exerted by vapors at equilibrium over the surface of liquid because the whole experiment setup was a thermostat, so what we will write, over the surface of liquid at a particular temperature. So now we can define vapor pressure. The pressure exerted by vapors at equilibrium over the surface of liquid at a particular temperature. Now the factors which affect the vapor pressure. What will be the factors which affect the vapor pressure? Okay, before going to discuss the factors affecting the vapor pressure, I am writing it as Vp, that is the vapor pressure. Okay, right. So the vapors escape out from the surface of the liquid. It means if the liquid molecules are tightly bound, what means there is strong intermolecular forces between the liquid molecules. It will not be easy for the molecules to escape out in the form of vapors. It means the first is nature of liquid. That is, if the intermolecular forces between the second factor which affect the vapor pressure is temperature. Okay, so if we cut the onion, then you get tears in your eyes because of the chemicals which get evaporated. They bring the tears in your eyes. So but if you keep the same onion, I usually do in my routine life, if you keep the same onion in ice cold water, you will get less tears. Why? Because of the low temperature. So what I want to say, the temperature will be higher, then there will be more kinetic energy in the molecules of the liquid. It means they will get easily vaporized. So I give you example of onion. So when you keep the onion in ice cold water, the vapor pressure decreases, and you can cut the onions in a better way, like having less tears. So temperature, I hope you have understood that more the temperature, more will be the high vapor pressure due to the increase in kinetic energy. Okay, so now we will discuss the topic related to the vapor pressure of solution. That topic is Raoult's law. So we have discussed the what is vapor pressure, the factors which affect the vapor pressure. Now if we take the liquid, as we discussed this experimental setup, in a closed container, then suppose we take the liquid solution, right? Liquid solution, that is the mixture of two components. Suppose component A and component B, right? A plus B. So we get the vapors of both components, that is here the components A and component B both will be there and both will exert the pressure, and the pressure which is exerted by the vapors of A, say that is the PA. PA will be equal to, PA is, what is PA? Partial vapor pressure of component A, that is PA is partial vapor pressure of component A. Similarly, PB will be partial vapor pressure of component B. Here comes the Wright's law. In 1886, F.M. Raoult observed that partial vapor pressure which is due to component A is proportional to mole fraction of component A in the liquid phase. Similarly, the partial pressure that is PB, the partial pressure due to component B is proportional to XB, that is mole fraction of component B in the liquid phase. And he also observed that means partial pressure due to component A is the mole fraction of component A multiplied by the vapor pressure of the component A at its pure state, that is XA multiplied by PA naught. PA naught is vapor pressure of component A at its pure state, right? At its pure state. Similarly, PB will be equal to XB PB naught, and similarly PB naught will be vapor pressure of component B at its pure state. Now here comes the Dalton's law. You know, according to Dalton's law, so this is the Wright's law, mathematical presentation. Wright's law, and you know, according to Dalton's law of partial pressure, total pressure P will be equal to partial pressure of component A, PA plus PB, right? And we can write it as XA PA naught plus XB PB naught. This is according to Royle's law. Right? Now, as you know, XA and XB, these are the mole fraction, and you know XA and sum of XA and XB is always unity, that is the XA plus XB is equal to 1. So we can write here instead of XA, but we can write 1 minus XB PA naught plus XB PB naught, right? Because XA plus XB is equal to 1. Now, if we see this equation, 1 minus XB PA naught plus XB PB naught. XB is the common here, right? So we can, okay, I can make it more simplified. So first of all, we can write this PA naught minus PA naught XB plus XB PB. It will be more easy for you to understand. Okay, now XB is common here, so we can write it like this, XB, and we will write it PB minus PB naught minus PA naught, and here we will left with PA naught. This is the total vapor pressure. Now, if we will look at this equation, because PB naught, PA naught and PA naught again, okay. So these are the constant value because these are the vapor pressure of a liquid at its pure state. It means the total vapor pressure is the linear equation of the mole fraction of the components XB, and we know XB is equal to 1 minus XA. So total vapor pressure is the linear equation of the mole fraction of the component in liquid phase. Now we will discuss how we will get the graph on the basis of this equation. So we will plot the graph vapor pressure and against the mole fraction. Right? So if the XA is equal to 1 and XB is equal to 0, as per the then the total vapor pressure, we discussed total vapor pressure is equal to PA plus PB, right? And PA is XA PA naught according to Raoult's law, right? So the total vapor pressure will be here PA naught only because XB is equal to 0. Now we assume that the component B is more volatile. So if the XA is equal to 0 and there is only component B, then the total vapor pressure will be only the vapor pressure of the liquid at its pure state, liquid B. It will be PB naught. Okay. So this will be the total vapor pressure at any mole fraction, right? So it will be P is equal to PA plus PB, and here it will be PB is equal to XB PB naught. PB is equal to XB PB naught, and here it will be this, it will be PA is equal to XA PA naught. So if we say this is the first equation, this and this is the second, and this is the third, then at any value of XA or XB, the total vapor pressure is given by this equation, that is P is equal to PA plus PB. Now this graph shows the vapor pressure of the liquid solutions which form homogeneous mixture, means the liquids which are completely miscible with each other, and the mixture, the liquid mixture which obey this Royle's law, that is PA is equal to PA plus PB, are called ideal solution. However, these ideal solutions are very limited, like the mixture of hexane and heptane, benzene and toluene, and chlorobenzene, and bromobenzene. So we were discussing that according to Royle's law, what we discussed, that the partial vapor pressure of component A is the product of the mole fraction and pressure of that component at its pure state. So we have discussed that with the help of Raoult's law, we can calculate the total vapor pressure of the liquid mixtures in which both the liquids are miscible and form a homogeneous mixture. So on the basis of this, we will calculate the vapor pressure of solution of chloroform by weight 25.5 gram and dichloromethane by weight 40 gram. And we are given vapor pressure of chloroform 280 mm of Hg. What is that? 280 mm of Hg, actually, if we consider chloroform as A, so means PCHCl3, that is the vapor pressure at its pure state is given 280 mm of Hg. And similarly, we are given P naught dichloromethane, that is equal to 415 mm of Hg. So according to Raoult's law, what will be the partial pressure of chloroform? PCHCl3 will be equal to mole fraction of CHCl3 multiplied by P naught, that is 280. Similarly, for partial pressure of CH2Cl2, it will be mole fraction of dichloromethane multiply by 415. You can write here the multiply. Multiply by 415. So we have to calculate the mole fraction of chloroform and mole fraction of dichloromethane. So how we will calculate? You know that XA, suppose mole fraction XA is equal to Na upon Na plus Nb, right? So we have to calculate first Na, that Na is number of moles of component A, that is chloroform, and Nb number of moles of component B, that is dichlorodimethane. So we have to calculate NCHCl3, number of moles of chloroform. Number of moles of chloroform, number of moles of formula you know, that is given mass upon molar mass. We have discussed in your 11th class this formula. Given mass upon molar mass. Given mass of chloroform is 25.5, and molar mass, for molar mass we have to calculate the molar mass of CaCl3, that is it will be 12 plus 1 plus 35.5 multiply by 3. So it will be 119.5. 119.5. And when we will calculate this, we will get 0.213 number of moles. Similarly, if we calculate number of moles for dichloromethane, that is 40 upon 12 plus 2 into 1, 2 plus 71. We get 40 upon 85, right? And the number of moles we will get, that will be 0.470 moles. Okay, so we have got the number of moles. Now we have to calculate the mole fraction. So now we have to calculate the mole fraction, that is XCHCl3, that will be number of moles for this, that is 0.213 upon 0.213 plus 0.470. So when we will calculate this, we will get 0.312 mole fraction for chloroform, and similarly mole fraction for dichloromethane. We will subtract it and we will get 0.688. Okay, now we have to put these values here and we will get the partial pressure of chloroform, that will be equal to, if we will multiply 0.312 with 280, then what we will get? We will get the value, that is 62.4. Here we will get 62.4, and similarly partial pressure of dichlorodimethane, we will get the value 0.688 multiplied by 415, we will get the value 285.5. So when we will multiply this, right, 285.5. Okay. So we were supposed to calculate the total vapor pressure. So for total vapor pressure, we will add 62.4 and 285.5. That is the total vapor pressure of the mixture as per Dalton's law. That is P will be equal to 62.4 plus 285.5, and we will get 347.9, that is mmHg, right? So in this way, using Raoult's law, we can calculate the total vapor pressure of liquid solution which are homogeneous, which make a homogeneous mixture.